So 1 million electron volts is 10 to the 6 electron volts, right? So then this cancels that. And if you do this in your calculator, you should get 0.511 million electron volts. It's called the rest energy of the electron. All right? And for the proton, the rest energy is on the order of 937 million electron volts. For the electron is just half a million electron volts. For the proton and neutron is more like 938 million electron volts. Close to this number. Now, I was talking about pair production, right? And pair annihilation. The first process was pair production. And in pair production, I'll just call this pair production. Right? So what we have here, so I like to think of the process in terms of a picture like this, and then from the picture, I write down the energy equations, conservation of energy equation. So you have a photon here, or energy, just a photon. Right? Let's say the wavelength is lambda, or the frequency is f, the speed of the photon is c, and then there's like a nucleus. So let's say this is a heavy nucleus. So this is a positively charged particle, and because of the protons in the nucleus are positive, the neutrons inside the nucleus don't have any charge, but it's just a nucleus. And then this is like, think of this as a collision, like when you were doing in Physics 185, there's a mass coming in, and then there's another mass at rest, and then they collide, and then they separate, and and then you say before the collision and after the collision. So this is before the photon interacts with the nucleus, and so this picture over here is before they interact, and then after, what do you see afterwards? So what's observed is that after the collision or interaction, you still have the nucleus, the heavy nucleus in there. Right? And let's say that the mass of the nucleus is m sub n, so this is m sub n. But then what's observed is that the photon is gone, and then two particles pop out. And one of them is an electron, where the mass is m, and the other one is it's a positron, which has the same mass as the electron. The only thing about the positron is that it has the opposite electric charge. So positron is like a positive electron. Think of this as a positively charged. By positive, one means positive in charge. The electric charge is positive, so it's a positive electron. You might say, well, doesn't the proton have the opposite charge of an electron? Yes. So a positron has exactly the same charge as a proton. But why is it not a proton? Because the masses are different. A proton is 1,836 times more massive than an electron. So the mass of a proton is roughly 1,836 times the mass of an electron. But the mass of that's a proton. The mass of a positron is exactly the same as the mass of the electron. So they are not the same particle. And this is actually an example of what's called antimatter or antimatter. So if you write down the energy balance equation, conservation of energy, what is the total energy before the collision or before this interaction? So the total energy would be what? The energy of the photon, incoming photon, plus the energy of the nucleus. Heavy nucleus, right? So what would that be? What is the energy of a photon? Well, the energy of a photon is what? It's Planck's constant times
lambda?
The frequency,
Oh,
hf. And the frequency is the speed divided by like the relationship between frequency and this frequency is the speed of the wave or of the photon divided by the wavelength of it. So you can write it as hc over lambda as well. And the energy of the nucleus, heavy nucleus, let's say at rest, it would be just the mass of the nucleus times c squared. That's the total energy before. Now, what is the total energy after the collision? So the total energy after the collision would be the energy of the nucleus. So that's the energy of this plus the energy of the electron plus the energy of the positron. But what is the energy of the nucleus? So the nucleus, the reason why one says it's heavy is because it's not observed to really have that much kinetic energy in it. So it's roughly, roughly at rest or moving very, very slowly. It's really there to conserve linear momentum. And so it's just, you still have the mass of the nucleus times c squared plus. Now, what would you say is the energy of the electron? Well, the energy of the electron is you can think of the total energy. One of the equations that Einstein used for the total energy, right, is that you can think of this as mc squared plus the kinetic energy. Right? So, in that spirit, the total energy of the electron is the mass of the electron times c squared plus the kinetic energy of the electron. And for the positron, the total energy of the positron would be the rest energy of it plus the kinetic energy of the positron. So this is not a formula that I memorize. I mean, I think of, you have a photon coming in and interacts with a nucleus. I just remember that you think of the nucleus as pretty much being at rest. And then the photon is gone. The energy of the photon just materializes into two particles, a particle and an antiparticle. And then you still have the nucleus in there. You don't have the photon anymore. That one is gone. And then you have these two particles. And what is the total energy of this? And what is the total energy of that? And then you just equate the two energies. Here I have a photon. The energy of a photon is hf. And I have a nucleus at rest, so mc squared. And what about over here? Well, I still have the nucleus roughly at rest, so it's mc squared. And then I have the energy of this plus the energy of that, which can be written in terms of their rest energies and their kinetic energies. And notice that if I equate these two energies from just conservation of total energy, if I equate these two, then the energy of the nucleus goes out. And then I have a relationship between the energy of the incoming photon and the rest energies of the electron and positron. So mc squared for each one of them, they have the same mass, so it's twice mc squared, where m is the mass of the electron or the mass of the positron since they have the same mass, plus whatever kinetic energies the electron and the positron have. Maybe I'll just write positron. People like to call it E plus and the electron E minus. So it's sort of like, I like to think of this event like this. A photon comes in with $2 million. Okay? The nucleus has some money, I don't know, $1. Whatever. I mean, it's more than, whatever. Let's say $1 billion. All right? And then, what do we have at the end? Well, you still have the nucleus, so that's $1 billion, right? And now, the $2 billion of the photon went to create these two particles. So it'll be shared between them. The amount of this will be 0.511 million dollars, and the energy of this, because it has the same mass, the rest energy is 0.511 million, how much energy do we have left over? So essentially, it's like the nucleus is out of the discussion. The $2 million, out of the $2 million, half, roughly a little bit more than half of $1 million went into making the electron, and roughly a little bit more than half of $1 million went into making the other electron. So how much energy do we have left over? So we have, it's like 2 minus twice 0.511, right? Because, and then whatever you get, that's going to be the kinetic energy together of the electron and the anti-electron and the positron. So if I ask you, what is the minimum amount of energy or the minimum amount of money that the photon needs to have if it is going to make an electron and an anti-electron? That's the minimum amount of energy. That would be the amount of energy that will lead at the end to the creation of an electron and anti-electron, a positron, both of them at rest. So how much is 0.511, 0.511? So this is 2, 2, 1.0, right? So, MeVs. So if this photon has an energy of 1.022 million electron volts, then when this photon is gone, disappears, it's out of existence, right? Then this energy, half of that energy will make this electron, and the other half of that energy will make this positron. But if you add the energy of this, the rest energy of this electron and the rest energy of this positron, it will be exactly equal to that. In that case, the kinetic energy of this electron is going to be 0 because there's no energy left over, and the kinetic energy of this positron is also going to be 0. But if the photon coming in has more energy than that, then this is what will be used to make the electron and the anti-electron, just the material particles, right? The electron, the anti-electron, and any leftover energy will appear as kinetic energies. Yes?
How's that kinetic energy distributed for both of the
So in this process, usually because of the presence of the nucleus, what will happen is that this positron, right, usually is going to get a kick from this, so it'll end up coming out with a little bit more kinetic energy than the electron, because the electron is going to be attracted, and the electron is going to be slowed down by the heavy nucleus, and the positron is going to be pushed away. So just a little bit more, and But then, it'll depend on the process and other things, but roughly we can say, with what we have written down over here, that whatever extra energy the photon has, extra in addition to the energy necessary to at least make these two particles, right? Then that extra energy will go and, distribute as kinetic energies between both of them. And if you measure the kinetic energy of one of them, then you'll know what will be the kinetic energy of the other one, if you know how much energy this one had. But this formula that you see in my notes, somewhere in here, this one, is not a formula that I go around memorizing. I don't want to memorize something like this. Give me a minute, and I'll just think. A photon comes in, you have a nucleus, the nucleus is there at the end, so the energy, the nucleus isn't really taking much of the energy of the photon, and so then the energy of the photon gets converted to the energy of the electron and the energy of the anti-electron, of the positron. So I can just think of HF, the energy of the photon, this is the sum of the rest energies of the electron and the anti-electron, and then any leftover energy is just the kinetic energies of both of them. But then the question is, what is the minimum energy that the photon needs to have? So, it needs to have at least 1.022 million electron volts of energy. If you consider the photon energies of visible light, right? For red light, the photon energy is on the order of 1.5, 1.6, 1.4, 1.4, not millions, just 1.4, like $1 and a few cents, electron volts. And for violet light, it's like 3.2 electron volts. That's it. like, $3. Here we're talking about over $1 million just to make the electron and the anti-electron. So that's why these lights, these sources of lights, don't produce electron, anti-electron pairs in this room in our vicinity, right? So they need to be very, very energetic photons, gamma rays. But that's all there is. I mean, there must be a homework problem, and then the question is, notice, if you want to know the minimum energy, the minimum frequency, for the minimum frequency, that would be the minimum energy in the photon. Then you want the minimum frequency. Now, because the frequency is the speed of the wave divided by the wavelength, so if the frequency is the lowest, what must be true about the wavelength associated with that photon? It has to be the largest, right? So this would be like the maximum. So any wavelengths lower than the maximum will correspond to higher frequencies than this, and so the electron and the positron will go off with kinetic energies. Right? Anyway, now, what happens in the, so usually in the homework problems, you're told, what would be the maximum wavelength of a photon or radiation associated, that would result in the creation of a proton-antiproton pair. Then you look up the masses of the proton, which will be the same as the mass of the antiproton, and then calculate this energy, and then then you just plug and chug. So this process over here involves, this is pair production. A pair of material particles are produced out of pure radiant energy, like magic.
So, what do you mean by the E minimum photon?
So suppose I say, okay, I want radiation to, let's do this problem. I want radiation to create a proton and an antiproton. Well, it has to be the minimum energy of that photon that will create a proton and an antiproton.
That electron, proton.
Yeah, so let's change the numbers. A proton and an antiproton. How do you calculate the minimum energy that a photon needs to have to create a proton and an antiproton pair? Well, if it has a lot of energy, it'll make the pair, and any additional energy necessary to just make the pair will go as kinetic energy of the particles, right? But I want the minimum energy. So it'll be just the energy necessary to make the pair of particles. Yes? It has to make sense. Don't fall asleep tonight unless that makes sense. Yes? So the energy of the photon has to at least make the proton plus the antiproton. The proton and the antiproton, they both have the same mass. Okay? And then plus, I can say this is the proton, like proton, antiproton. If the energy of the photon, I tend to call it gamma, if the energy of the photon is more than this, any additional energy will show up as kinetic energy of the proton plus kinetic energy of the antiproton. But if I want the minimum energy, then I don't want them to have any kinetic energies. Yes? It's like, your little brother is gonna buy a In-N-Out cheeseburger for, I don't know, $3.45. And you just give them $3.45. You don't give them any more than that. You're not gonna have any leftover money to buy anything else. I'm just gonna give you that and that's it. So just to make them, right? So this would be, sorry for that. I don't know if you have a little brother and but I hope the message gets across. So then you look up what is the mass of a proton. What is it? 1.67 times 10 to the minus 27? I think, I don't know, I have to look it up. But maybe one of you can Google it. And then this is 3 times 10 to the 8th, and we have to square that. But this will be in joules, right? And so 1 electron volt is 1.6 times 10 to the minus 19 joules. That cancels this. And then 1 million electron volts is 10 to the 6 electron volts. So the electron volts cancel. And I'm gonna get an answer in million electron volts. And it's something around 938, 37, something like that. Maybe one of you can help me out. Let's say that's the answer. Actually, it should be twice that, because that's the energy of one of them. So how much is twice 9? So this would be like 1.876, right? Oh, but yeah, because it's twice that. Because this is the rest, roughly this is the rest energy of one of the proton or of the antiproton. Should be like 1.876. Let's make it 1.8. Well, that would be billion now, right? In that case. Or 1.88 giga electron volts. That's what the energy of the photon should be, the minimum energy. Now, what if I wanted, so I'm thinking of a photon coming in, right? The energy is E gamma, and there's a nucleus. Something happens, and the nucleus is there, and then you have the proton and antiproton. Right? So that's the mass of the proton, mass of the antiproton, same mass. So if I wanted to just make these particles without them having any kinetic energy, so I'll just like it made it, so it's just at rest. Not moving, at rest. So then this would have to be the minimum energy. Because I don't want that to be moving. Does that make sense? Now, what if I want to know what is the wavelength of this photon? Or of that radiation associated with that. So what is the relationship between the energy and the wavelength? Well, the energy of a photon is h times the frequency, right? But the frequency is the speed of the wave divided by the wavelength. Now, if this is a minimum, that means that the frequency is going to be a minimum, but if I want to minimize the frequency, I have to maximize the wavelength. So the wavelength has to be either some value or less than that value, smaller than that value. If it's equal to that value, it'll just make the particles without endowing them with kinetic energy. But if the wavelength is even shorter than that minimum value, well, any leftover energy will appear as kinetic energy of these two particles. But it's not a formula that I memorize. I just think of total energy before, total energy after, and I equate them, and then I know what the expression is that relates the energy of a photon to its frequency and its wavelength, and I know what the energy is to express the energy of a particle to its rest energy and its kinetic energy. That's what I need to know, and then I can write this up.
Why did you do 2 times?
Because this is this.
Oh, okay.
Roughly, I'm kind of going by memory. It might be 936.7, but it's around there. I just don't remember what it is exactly. I kind of remember what the number is for the electron, but not for the proton. So it's almost like asking, what is the minimum energy that a photon needs to have to make you? Exactly. The photon is gone. So in the beginning there's a photon and there's no you. And afterwards the photon is gone, but there's you. But if I want the minimum energy of the photon, it'll just be enough to make your mass. So it'll be your mass multiplied by the speed of light squared. But what if the photon has more energy than that? Then it'll make you and you'll be running. Because you'll have kinetic energy. No? Okay. If you figure this out over here, these energies of these photons are so big that you have to be talking about gamma rays. You're in the region of the electromagnetic spectrum, where you find gamma rays, not visible light. Now, what if